In this problem, we are asked to determine the load function for a simply supported beam that's subjected to a linearly varying downward load. From the free body diagram, we see that there are going to be upward reactions at C and H. Note that the magnitude of the triangular load is going to be half PL, and that the distance of the effective line of action of force is going to be 2L over 3 from D. Summing forces in Y, we will have Cy plus Hy minus half PL is equal to a 0. Summing moments about point H, we'll have minus Cy times L plus half PL times L over 2 plus 2L over 3 equals to 0, which gives us Cy equals 7 over 6 PL. From equation B2, we will have Hy equals to a minus 2 over 3 times PL. The next step is to try and derive the load function for the triangle through linear operations. What we have on the top is the desired shape function. The first step to derive this might be to draw a straight line with a negative slope, whose equation in terms of Macaulay function is given by minus P over L, which is the slope of this straight line, multiplied by x minus 0.5L to the power 1. When we have this as our input, our output ends up looking like that. Now what happens if we add on a straight line with a positive slope, whose equation is given by P over L times x minus 1.5L to the power 1. Our output then changes to a straight line after 1.5L, because this straight line and that straight line combine to give a horizontal line. The desired shape function, however, is this. It still needs to be shifted up by p units to resemble the desired output. How are we going to accomplish that? Let's go ahead and draw a unit step function whose height is equal to p and which starts at 0.5L. Its equation is going to be given by p multiplied by x minus 0.5L to the power 0. When we go ahead and combine these three straight lines, the dotted lines, we will achieve what is our desired shape function. The desired shape function for this triangle is given by the linear combination of these three dotted lines, which is equal to a p times x minus 0.5L to the power 0 plus a p over L times x minus 0.5L 1.5L to the power 1 minus a p over L times x minus 0.5L to the power 1. However, the triangular load that is applied is actually downward, whereas the equation that we derived down here, is one for an upward load. So all we need to do to accommodate that change is put in a minus sign. Let's now scroll back up to our free body diagram and try to write out the load function in terms of the reaction forces. If we call that P2x, we'll have P2x equal to a Cy multiplied by x minus L raised to a negative 1 plus an Hy times x minus 2L raised to a negative 1. Let's go ahead and call this P4. Notice that adding this hy term makes no difference to the answer when going from the left hand side to the right hand side. This is because the maximum value of x that we could have is x equal to 2l, in which case this hy term goes to 0 anyway. So the total load function px is going to be given by the sum of p1x and p2x. We can therefore write out px to be equal to p1x that we have from equation p5 plus p2x from equation p4. This concludes our solution to problem 8.1b.